Okay, hi everybody. Today we're going to start with a demonstration of some heat that is being evolved or used in a chemical reaction. In this case, our chemical reaction is going to be the dissolution of a couple of chemicals. The first chemical that we're going to dissolve is going to be ammonium nitrate, and we're going to dissolve it in 100 grams of water. And I am putting 3.3 grams of ammonium nitrate into there. Now, what I am going to do is I'm going to take the temperature of my ammonium nitrate or of my water. So there's my 100 grams of water, and I'm going to go ahead and take that temperature, and I'm going to wait for that temperature to equilibrate itself. So if you want to be able to see what this is looking like on the screen right now, this is what it's looking like on the screen. I'm just waiting for it to come to a steady temperature, and we are going to be able to see what that looks like. So I'm actually going to set it up so you can see the screen going on right there, and you can see the graph happening right there. So what I'm actually doing is I'm going to, I don't know if you can see, there it is right there, and I'm going to pour my ammonium nitrate into my calorimeter, and I'm going to use my thermometer as my stir rod, and I'm going to record what happens to the temperature as we get started. So the first one is going to be ammonium nitrate, and I'm going to go ahead and click collect, and so you'll see that I'm immediately collecting a set, and you can see we've equilibrated to the to a constant temperature. And so I'm going to go ahead and get myself a profile of the platform of where we are starting, and then I'm going to go ahead and add all of my ammonium nitrate to my solution, and I'm going to stir. So in the process, I'm stirring, and I am trying to see basically what is going to happen. And I'm going to stir, and I'm going to, and I don't know why that just came up, but we'll let that be. We're going to see what happens here as a result of the whole process. And as you can see, we have already gotten to the end here, and we already have hit a bottom temperature of this reaction. And so what I'm going to do with that is I'm going to actually make the screen bigger so you can see it. And what we have is a temperature profile over time here. So what I want to do is I want to be able to have you look at, okay, exactly what is this telling me? So this is telling me that, in fact, I had a pretty constant temperature to begin with. And then my temperature started to go down quite a bit. And then I had pretty much a leveling off of the temperature at the end, with basically the lowest temperature being down here at the end. And so we have to ask ourselves, well, what is going on there, and what do we need to know? What is that telling us? And for those of you that are going, oh, I know that is going to be a endothermic reaction because temperature decreased. And you are right. So we would have to be able to solve the Q equation for how much energy was absorbed by taking our mass of our water, and I'm doing something that I probably shouldn't do, mass of the water, which was 100 grams, and I'm going to multiply it by my specific heat capacity of the water, which was 4.184, and I'm going to multiply it by my temperature change. And my beginning temperature was 20.4, but my ending temperature down here, which was my lowest temperature, came out to, let's see, all the way to the bottom here, 17.5. So I'm going to have 20.4 minus 17. Actually, I did that backwards. Let's write it out. That should be my final temperature as 17.5 minus 20.4. And you automatically know right away that that means that we are going to have a negative Q. So my negative Q is going to come out there, and that is going to happen because what we have is an endothermic reaction. We'll get a negative Q. In other words, the water lost heat. Now, the water did not lose heat to the surroundings, and the reason you know that is because the temperature was pretty stable at the top. The water actually lost heat to the chemical change happening in that we were dissolving the ammonium nitrate into the solution. Okay, so then we want to know, well, what does that come out to, and how much molar heat was actually done? And so we're gonna go ahead and see if we can do those calculations right now. Okay, so our calculations give us a total of negative 1,213 joules. And if we change that to kilojoules, that is going to be negative 1.213 kilojoules. So then the last thing that we want to do is be able to divide it by the number of moles of ammonium nitrate that we used. And so that part is going to have to be the next calculation. Okay, so we are going to divide by the number of moles. And to get the number of moles, I did the mass of the ammonium nitrate divided by the formula mass of the ammonium nitrate. So this is what I get. And when I put all that into my calculator, negative 1.213 divided by 0.04, actually, let's make sure I do this right, 3.3 divided by 80.04. Okay, so I end up with negative 0.0046. That does not come out right. Hold on. When I do my math, it actually comes out to 30.3 kilojoules per mole that was lost, or you could say that was used in the reaction. Okay, so what if we have the opposite sort of reaction? What if instead we have an exothermic reaction? And that is going to be our next reaction that we are going to try. We are going to use, again, 100 grams of water, which, as you know, is 100 milliliters of water. But this time we are going to place into our 100 milliliters of water 6.6 grams of calcium chloride. That is 6.6 grams of CaCl2. And so we are going to tell it that we want to erase. And we're going to erase and continue. There we go. And we have started our temperature. It is currently at a temperature of 21.3. Let's make sure that we have a good picture of what is going on. And we're going to like that. Nope, we don't want that. Okay, it looks like that right now because my scale is quite a bit larger than what we have, and so it is still adding, but I'm going to go ahead and add my calcium chloride to the solution. So there is my calcium chloride, and I'm going to try not to cover everything up. And currently it is going up and up and up and up. And I'm going to want to have, it rescale itself. There we go. And as you can see, it is still doing its thing, giving it time to finish. It is still going up in temperature. I think we might be getting pretty close to the end here. This is the calcium chloride is actually a compound that gives you the ability to clean off ice on your driveway. If you have ice on your driveway, when you react it with water, it makes heat. So it is used as a de-icer. Right now we're at 29 degrees, so we're still going up and up and up. I need to change my scale again. So we're still going up and up and up. And as you can see, it is looking like it is beginning to plateau out. So we're going to let it sit for a bit and see if we get anything else here. We're going to rescale that so we see what all's happening. It does look like we have plateaued out at 29.6. I'm going to give it a few more seconds here for it to finish up. It naturally is going to stop at 300 seconds. So I did add in a few more seconds for it to do, and you might notice that in fact the temperature is now beginning to go back down again, and so I am giving it time to finish up things. I'm going to let it Okay, letting it go there for just a little bit so you can see what is going on. And this is a typical heating curve that you might see for a spontaneous reaction like this. And I only stirred it to make sure that we would get an even distribution of particles throughout the solution. And so I think we're kind of right there as far as how far does this reaction go. So I'm going to go ahead and stop my reaction. Now, one of the things that we hear of sometimes is that we have to be aware of also heat being lost to the surroundings. So heat being lost to the surroundings, in other words, coming out the top of the cup. Okay, so once we have our data, the question becomes, have we lost any heat to the outside air? Because as you know, the top of our cup is open, and so the way we determine if we've lost any heat to the outside air is we use our graph and we draw a line that is adjacent to the top line here. And I'm going to draw it across to where it crosses there. And then this one, okay, so I draw myself a little T on here so that you can possibly see that too, yes? And what we're looking for is, well, what temperature is actually the highest temperature that we attained? And so I know that we can look for the highest temperature that the laboratory got to by scrolling down here, because the highest temperature, I'm trying to grab this, the highest temperature our laboratory got to was 29.6. 29.6. And this might actually be at 29.6. But if there had been a lot more heat that was released, then this parallel would have been down like this, and we would have been up higher here. So this would give us, this intersection right here would tell us the actual point right there. And that still looks like that's at 29.6. So again, we're going to do the calculation. We have our initial temperature was 21.2. Let me check that and make sure that that was our initial temperature. Our initial temperature was 21.2, and our final temperature was 29.6. So we have 100 times 4.18, 4 times our final, which was 29.6, minus 21.2. And we know that the temperature has gone up, so our Q here is going to be a positive Q. Our overall reaction then has produced heat in the amount of 3.515 kilojoules. So the last thing that we are going to want to do is we are going to want to find out what is the what is the number of moles, and therefore what is our molar heat. And so I am going to, and I'm trying to find my information here. There it is. Okay, so I'm going to do dividing it by the moles, which is 6.6, divided by the formula mass, which is 110.99. Okay, and when we do that math, we get 59.6 kilojoules per mole. And so that is our pretty standard type of reaction that we get for not only the heat that is released in this example, but also the molar heat of the reaction of this dissolution. Molar heat of dissolution is what this is called. Okay, so the next part we're going to do is basically our laboratory. Okay, hi everybody. Today we're going to be doing a laboratory, which is a calorimetry laboratory with 3 different metals. And the 3 different metals that we're going to be using are aluminum, brass, and copper. All right, so those 3 metals are going to be the ones that we are going to heat in our beakers. So you can see our beakers on our hot plate here. Those 3 metals are going to be the ones that we heat on our hot plate. And to be able to do this, we need to make sure we're following the directions here. I have filled my metal containers with the appropriate amount. These are going to actually be my calorimeters. In the past, we have used styrofoam calorimeters, but these metal calorimeters have a cover on top of them, so they will solve the problem with heat being lost to the outside air. And so for the most part, we're going to keep it all in here. We are, as you know, using the beakers where I have somewhere around 200 milliliters of water added in there, and I'm just waiting for the water right now to start boiling. And so while I'm waiting for the water to start boiling, I have gone ahead and taken the masses of my blocks so that we are able to calculate some moles later on. So my aluminum block actually has a mass of 47.15 grams. 47.15 grams. And I'm going to go ahead and add my aluminum block to the beaker that is currently boiling and get that one going on. So I'm going to do that. And then, and I'm going to let these all boil together for about a half an hour, not a half an hour, more like about 10 minutes or so. So my aluminum is in there. Then I've taken the mass of my brass, and the brass has a mass of 138.79 grams. And we're going to go ahead and add that brass to the liquid as well. We're going to let that heat and hopefully get started boiling here real soon. And then I've taken the mass of my copper, which is 145.71 grams. And I'm going to go ahead and add my copper to my beaker as well. So all three of my metals are now currently heating. And so while we're allowing the metals to currently heat, and we're going to take the temperature of the water so we can know when to stop, because the directions say to heat them until the temperature is a temperature above 90. And so right now my aluminum, and I'm going to go ahead and take this temperature and find out for you. Actually, I'm going to do this particular temperature with the temperature probe, because that makes so much more sense and goes so much more quickly. So here is my temperature probe, and the aluminum right now is at a temperature, and it's going up super fast. I'm going to tell you just in a second. Notice I'm holding it up. I am not letting it rest on the bottom, because resting on the bottom or touching the aluminum would be giving me a different temperature. So right now I have about 96, 97.2 in that one. In this one, I have more like 91. And in this one, I currently have more like about 80, 90, also 92-ish. Okay, so I'm going to let those boil for just a little bit. We'll get some final temperatures of that. While we are letting those boil, we are going to make a data table. So on your own paper, maybe on a separate Google document for you, maybe at the end of this document, it is your choice. You are going to make a data table that will hold all of the information. So far, you have the information about the masses. So the aluminum, again, was 47.15 grams. The brass was 138.79 grams, and the copper was 145.71 grams. And so we are letting these heat. I'm going to take a final temperature of each one so you know what this is going to represent the starting temperature of the metal, and we are going to need to take a starting temperature of the water. So far, our data table will need the masses of each metal, the identities of each metal, the starting temperature of each metal, the starting temperature of the water, and then we're going to have an ending temperature of the water, which will be the same as the ending temperature for each metal, because we're going to put it all together and they will equilibrate. In other words, they will come to the same temperature, thermal equilibrium. Okay, so while they're heating, you're making a data table, and so we're going to do this for 3 different metals and pretty much at the same time so that we can record all this data at the same time. Okay, so what we want to be able to do is we're going to remove the metal from the hot water, dab it off on the paper towel. So I'm getting myself some paper towel here so that we don't take any hot water with us into the calorimeter. We don't want to add any hot water. Oh, the other thing that you need to know is that the water in the calorimeter is a total of 100 milliliters in each calorimeter. So when we are calculating Q, we are going to use the mass of the water, not the masses of the metals. The masses of the metals will be used later for when we want to calculate moles of metal that we put in there. But for right now, we're just going to focus on Q as right now. So our mass of our water will be equated to 100 grams because 100 milliliters is the same as 100 grams of water. And while we're waiting for this last little bit of heating to go on, I can report that the initial temperature of aluminum's water is going to be 10.1 degrees Celsius. The initial temperature of brass, the water in the brass, is going to be 14.5 degrees Celsius. And the initial temperature in the copper is going to be 19.0 degrees Celsius. So once again, 10.1 degrees Celsius for initial temperature of the water of aluminum, 14.5 degrees Celsius for initial temperature of the water in the brass, and then 19.0 for the initial temperature of the water for the copper. Okay, so I'm about to move things now, and so I want to know what is aluminum's highest temperature. That aluminum is starting temperature for aluminum, and it is going, I really don't want to use this. I really want to use the temperature probe because it is so much easier to just use the temperature probe. So the starting temperature of the aluminum is, and it's going up, it'll tell us in just a second. (98.5) is the starting temperature for the aluminum. I'm going to take the aluminum out and I'm going to dab it off on the paper towel, and then I'm going to put it directly into the calorimeter with the aluminum's water, and we'll record that. The next one is going to be the starting temperature for the brass, and we're going to go ahead and take that temperature right now. (98.2) is the starting temperature for the brass. Also going to dab that off right here, and I'm going to add that to the water for the brass. So right now I'm adding it to these waters here. And the last one is going to be my starting temperature for my copper. And we'll wait for the starting temperature of the water for the copper, and then we'll go ahead and add that in as well. And then we'll take the final temperatures of each of these in just a moment. Okay, starting temperature for the copper is 98.2 as well. Okay, here you go, copper. And I've just found out that one of my thermometers is broken, so I'm going to use the temperature probe for that thermometer. So that was my aluminum thermometer. I'm having to switch over to a temperature probe, and I'm moving copper, which the starting temperature for the copper was 98.2. Are these all having problems? Okay. Okay. Okay, I can tell you, and then we're going to wait. We're going to give this some time to think about things. That one's broken. Let me see if I can use a different thermometer for this. I don't really want to use the temperature probe for that. Okay. Okay, we're going to give it a few minutes, and then we're going to come back and check. Okay, so our highest temperature for our aluminum reached a highest temperature of 26 degrees Celsius. Brass reached a highest temperature of 23 degrees Celsius, and copper reached a highest temperature of 29 degrees Celsius. So that means that what you need to do at this time is complete filling in your data table with all of the parts that you need and calculate all of the analysis questions. So you should show work for all of your calculations. It says calculate the experimental specific heat capacity for your metals, showing all of your calculations. Report your process data in a data table properly labeled. So let's talk about that. You can make a second data table with having all of the data, including the raw data that we measured and the calculated data that we just calculated, or you can make a separate table that holds just the calculated data and the original data table holding all of your measured data. It's up to you. Please make sure that all of the unit labels are provided. At this time, we are not going to worry about uncertainties. We are just going to worry about you having unit labels. So let's go over that. The temperatures are degrees Celsius. The masses of the water was in grams because we converted it from milliliters. That means that you are going to be calculating using water's specific heat capacity in joules per grams degrees Celsius. So make sure you use the right number for that. Then you are going, once you've calculated the Q, not the Q, the specific heat capacity for each one, then you are going to be able to compare that to a standard value, which you're going to need to look up. So since you're going to need to go look up each metal's specific heat capacity, please make sure you cite the URL that you got it from, each metal's specific heat capacity, and you're going to do a % error calculation so that you can say how far off we were. Now you might be going, well, wait a minute, how am I going to know Q? I don't know Q. You're right. So you're going to have to find Q by using the information given in the background information of this laboratory. And if you go back and look at the background information of this laboratory, the important part that you need to use is right there where it says Q for the Q lost by the metal is equal to the heat gained by the water. So that means the metal is going to be losing heat. In other words, it should come out as a negative number. Remember, final minus initial temperatures. The water should be a positive value because the water gained the heat. It's also doing final minus initial. So keep that in mind. If you can calculate the temperature change amount of energy for the water, then you can use that as your Q, but change the sign so that you can solve for the missing specific heat capacity of each metal. You should have a specific heat capacity for aluminum, one for brass, and one for copper, and then you should have a % error for each of those as well. Then you're going to need to talk about, well, what kind of errors might we have had? Okay, everybody, that is what you need to get done. Thank you.